So now we're going to pull it all together. We're going to pull together balancing reactions, converting moles to grams, converting grams to moles, and theoretical yield all in one problem. And the problem that I've selected is, incidentally, the reaction that goes on in crystal Drano. Crystal Drano is a material that's used for clearing a stopped up sink. I would have shown it to you, but unfortunately we have everything on the set but the kitchen sink. It's the reaction of aluminum solid, sodium hydroxide solid, and water that happens to be sitting around in your drain, and it forms sodium tetrahydroxyaluminate and hydrogen gas. And this turns out to be a reaction that gives off a tremendous amount of heat as the reaction proceeds. That's good for melting the grease that might be stopping up your sink. It's a very basic reaction. It has sodium hydroxide. That's good for helping to hydrolyze proteins and things like that, like hair that might be down your drain. And it also gives off a bunch of gas, and that helps to loosen everything up and get things going as well. So suppose we begin with 7.75 grams of aluminum and 8.00 grams of sodium hydroxide and 100 grams of water. And if we, instead of doing the reaction in the kitchen sink, did it in a laboratory, collected the hydrogen gas and could weigh the hydrogen gas and discovered that we obtained 0.541 grams of hydrogen gas, what is the percent yield? And again, to do this problem, we're going to have to take this reaction, which is unbalanced, first balance it, then convert these masses into moles, use the balanced reaction and the mass and the moles of each of our reactants in order to determine the limiting reagent. And then from the limiting reagent and the actual quantity of product we obtain, we can get a theoretical yield. We can get a percent yield. All right, so let's balance the reaction first. And here's the reaction. And you'll recall that I said, as a hint, when you're going to balance a reaction by inspection, start with the compound or molecule that has the greatest diversity of atoms. Here we have something that has 4 different kinds of atoms. Let's start there. And the way you start is you put a 1 somewhere. So we're going to put a 1 there. And then I said, go to the other side of the arrow and go to one of the 2 the first reactant on the reactant side and balance for that element. In this case, it's aluminum. But I also said, why don't we go ahead and try to leave the pure elements for last? So let's start with sodium instead. We have 1 sodium on this side, so we'll put a 1 here. That balances for sodium. And now let's balance for hydrogen. We can't do hydrogen. We'll do oxygen. We have 4 oxygens on this side. Remember, 1 atom per hydroxy, and we need 4 of those, so there are 4 oxygen atoms. We have 1 from the oxygen in sodium hydroxide, so that means we need 3 waters. So that now we have a total of 4 oxygen atoms on the left-hand side to balance the 4 oxygen atoms on the right-hand side. Now let's go ahead and do aluminum. We have 1 aluminum on the right-hand side, so it means 1 aluminum on the left-hand side. And finally, we'll do hydrogen. We have 1 hydrogen atom plus 6 more hydrogen atoms for a total of 7 hydrogen atoms on the left-hand side. We have 4 hydrogen atoms in the tetrahydroxyaluminate, and so that means we're going to need a total of 3 more hydrogen atoms, and so that means that the coefficient on hydrogen is 3/2, because remember, 3/2 times 2 means 3 hydrogen atoms plus the 4 makes a total of 7, and we have 1 plus 6 is 7. So this is a balanced reaction. And then finally, you'll recall that I said, let's multiply by a factor in order to clear all the fractions. And so if we do that, we have 2 aluminums plus 2 sodium hydroxides plus 6 waters going to form 2 formula units of sodium tetrahydroxyaluminate and 3 moles of hydrogen. So this is a balanced reaction now with integral coefficients. And we're going to use this. Now, the first thing we need to do on this problem is we need to determine what is the limiting reagent. And here we have 3 different reactants. So I suggested that method 2, where you calculate the expected amount of product for each of the reagents, is the easier way to go. So let's do that. First, we have to calculate how many moles of reactants we start with. So here's the number of moles of aluminum. It's the mass of aluminum times 1 mole over the molar mass of aluminum. and that gives us 0.287 moles of aluminum. We repeat this process for sodium hydroxide and for water, and these are the numbers of moles of each of the reactants. Again, these are based on the number of grams of reactants that we started with. And then, using method 2, we calculate the number of moles of product, and in this case, since we're concerned with hydrogen, let's focus on that. Remember, hydrogen is the product that we actually collected, so that's what we're going to be interested in. Moles of hydrogen is 0.287 moles of aluminum times the conversion factor that relates the moles of hydrogen to the moles of aluminum. 3 moles of hydrogen for 2 moles of aluminum. Let's go back and look at the balanced reaction. We can see 3 moles of hydrogen for 2 moles of aluminum. So that's where the 3 and the 2 come from. 3 moles of hydrogen for 2 moles of aluminum. And so we multiply through here and we get 0.430 moles of hydrogen. And similarly, from the number of moles of sodium hydroxide we started with, here 3 moles of hydrogen for every 2 moles of sodium hydroxide. Go back and look at the balanced reaction. You'll see that's correct. So we multiply through and we get 0.300 moles of hydrogen. And then for water, 5.56 moles of water times 3 moles of hydrogen for every 6 moles of water, and that gives us 2.78 moles of hydrogen. Now recall, the limiting reagent in method 2 is the reagent that gives the least amount of product. In this case, it's sodium hydroxide. So sodium hydroxide is the limiting reagent. And furthermore, the theoretical yield of hydrogen is 0.300 moles. Right? It's neither of these two numbers because we'd run out of sodium hydroxide before we used up all the aluminum or before we used up all of the water. So this is the limiting reagent, and this is the theoretical yield. Okay, now the actual yield in hydrogen we have to get from the experimental data, the actual experiment that we did. Well, if you go back to the way the problem was stated, we can convert the number of grams of hydrogen that we collected, which was 0.541 grams, into the number of moles of hydrogen by multiplying by 1 mole over 2.2 grams, which is the molar mass of hydrogen, and that means that we actually collected 0.268 moles of hydrogen gas. And now when we want to calculate percent yield, we can calculate percent yield, which is the actual yield divided by the theoretical yield multiplied by 100%. And you'll recall that I said that you could express the actual yield in grams and the theoretical yield in grams, or you could express the actual yield in moles and the theoretical yield in moles. On the previous problem, we expressed everything in grams. This time, let's express everything in moles. So 0.268, which is the actual yield in moles. 0.300 was the theoretical yield in moles. Right up here, remember we determined this from the limiting reagent. Divide these two, multiply by 100%, and we get that a percent yield was 89.3%. So now that you've seen all of these concepts all wrapped up together, what you'll have to take my word for it is the only way to get good at these is to just do a bunch of problems. The mechanisms I've shown you will work for all the problems that you're going to encounter in this course, but you can watch me do it until the cows come home. You're not going to get it until you sit down, do a bunch of problems yourself. I can't encourage you more to just dig in.